So here we will be doing some substitution and elimination chemistry. So the first question asks you to find out which of these reactions would produce this compound here. So as you can see, it has a 1, 2, 3, 4, 5, 6 carbon chain, and we are looking at a substitution reaction where this is the nucleophile and here's the leaving group on the substrate. So you have a 3 carbon chain, so 3, and a leaving group bromine here, and you have the acetylide, which you have seen how to produce in chapter 9 or 10, yeah, I forgot, yeah, chapter 9 I think, right? So the substitution reaction is going to produce 1, 2, 3, 4, 5, 6, and that's essentially what we are looking at. So 1, 2, 3 carbon, and then a 3 carbon chain, the alkyne, right? So 1, 2, 3, 4, 5, 6. That's what option A is. Luckily it turned out to be the same one, right? Whereas here, if you look at this 1, 2, 3, 4, 5, this will also give a substitution reaction, but it will not be the same carbon chain. Here you have one extra carbon, 1, 2, 3, 4, 5, 6, 7 carbon chain, and that's not the right answer for that reason. And here, if you look at it, this does not have a lone pair for it to give you any substitution. There is no leaving group as well, so this is kind of an absurd reaction to begin with. So A is the right answer for this question. Okay, so which is possible product for the reaction shown here? So this is a base here, or a base and a nucleophile, but since this is a secondary bromide, there will be more elimination, right? Of course, they have given you all products that are elimination. Now we have to identify the right stereochemistry based on the anti-periplanar geometry that is required for this chemistry, right? So let's read out the structure. So here we have your leaving group. So you have a bromine. On the right hand side you have the methyl, left hand side you have the hydrogen, and on the right hand side you have a deuterium here, a hydrogen, and a CH3. Now both the hydrogen and the deuterium can be eliminated, right? So if you bring the deuterium to this position here, then you're going to have a molecule that looks like this: bromine, CH3. Keep the front carbon the same, whatever you have. On the back, if you bring the deuterium here, the deuterium comes here, the hydrogen goes here, and the CH3 goes there. So if this undergoes elimination, then, so that is basically the dividing line, and you will have a CH3 on the right hand side and a hydrogen here as you're looking at the molecule from this angle, and on the back you will have a hydrogen here, and on the front you will have a on the other side you'll have a CH3 for the left hand side. So this is one molecule, so let's write that. If from this conformation you put the hydrogen anti-periplanar to the bromine, then what happens is, let's erase these. So then if the hydrogen goes anti-periplanar, the hydrogen comes here, then the deuterium goes over here, and the CH3 comes over here. And now from here, again, if you draw the alkene on the front, if you're looking at this alkene from this angle, you're again going to have CH3 on the front to the right and the hydrogen to the left, whereas on the back you're going to have a CH3 here and the deuterium over here. So now we have to see which of these two structures you have in the answer here. So CH3, CH3, and deuterium hydrogen. So that is not there, which means you have to see if this structure is there. CH3, CH3 trans to each other, and hydrogen, hydrogen trans to each other. CH3s and CH3 trans to each other, and hydrogen and hydrogen trans to each other. So option D is the right answer.